why don't you tell me what you did first? I gave you a set of steps. What is the first step? All right, so what did you assume? Okay. I'm not sure why I'd go that route, but it really won't make any difference. Oh, that makes a lot of sense. Oh, well, that makes a lot of sense. All right, so assume charge. Good job. Thank you. Step 2, somebody else. Find the electric field. And if we set this equal to A and this equal to B, we're really only interested in the electric field between A and B. But anyways, what's that going to be? Yeah, again, not a whole lot to worry about here. So we now have the electric field. What's step 3? Somebody else. That's okay. Okay, so let's do that. We're going to find the potential, and we're going to go from the outside shell to the inside shell because we go against the field. And this is going to be of E dot dr.
It's really high.
Sorry, my daughter's bringing me a cup of coffee, which is going to be the best cup of coffee I've had today. But she filled it too high.
I haven't spilled any, so... Oh shit, yeah, I just did.
And she just spilled some.
It's fine, you can't even tell.
Thank you.
Mm-hmm.
Oh, I'm spilling it now.
Well, that's not my problem anymore. I didn't have coffee.
Well, I have coffee, so that matters. So this morning, just so you guys know what kind of day is already happening here, I had to have a PLC this morning. PLC. Yes, we still, as teachers, are supposed to be having meetings where we discuss, the finer points of what we do. I'm on one PLC that I was assigned to and one PLC that I chose. Most people have one or two. So there's one for the physics teachers. So you know who's in that one. Right, there he goes. And then there's one for there's one for all the AP teachers in science. And that one we actually have a lot to talk about, because we at least have the AP thing in common. But the other one, it's harder. All right, so let's go back to this. So we're going to do the integral of this. It's not a whole lot to do here, but it's a procedure. And that, to me, going through the procedure has merit. So we don't have to worry about the dot product too much because the direction of the field is, this way, and we are going from B to A, so we're definitely going against the field. And although this will give us a negative change in potential, this will give us a positive change in potential. It's negative work, but positive change in potential. We don't care about the change in potential so much. We care about what the expression for the potential difference is. So all of this comes out. We're left with the integral of 1 over r dr, which, somebody help me out with that. What is the integral of 1 over r dr? I'm sorry, yes. I might have just given away the answer. But what is the integral of 1 over r squared dr? There. Yeah, that's right, negative 1 over r. And I'm going to skip the negative and just put 1 over b minus 1 over a. We good to go? Now, here's where I would say, okay, we've got the first 3 steps done. We have our expression for the electric potential in terms of the charge. We got that from the field created by the charge, and we assumed how much charge was there. Capacitors work in the reverse, in that we apply an electric potential and that moves the charges. But we have to work the problem this way in order to get what the capacitance is, to get an expression for the capacitance. So our next job here is to take this expression and put it in the expression for full and critical. I should have put my negative sign here and made sure I used that correctly when I was doing my potential. In this case, remember, this is a dot product. This negative sign is a result of that dot product. If I had reversed the polarity of the charges, I wouldn't have gotten that negative sign because I would have been going the other direction with the field. But the capacitance. But the expression for capacitance is definitely going to put the electric potential in the denominator. And we have this weird subtraction of fractions. So before I do that, I'd like to express this as a single fraction, meaning I'm going to get common denominators so that this whole thing could be one fraction and will look better when I put it in the denominator. And I have a purpose for this that might lie in the fact that I've seen this problem before and maybe you haven't. So take this and get common denominators, which will give you ab in the denominator and a minus b in the numerator. Now the reason to do that is because then when I do my substitution here, I'll have q in the numerator, and in the denominator I will have q times a minus b divided by 4 pi epsilon naught ab. Which then can be rewritten as 4 pi epsilon naught ab in the numerator, all divided by a minus b in the denominator. Now, we have a problem with this, and Tyler's not going to like it. Where's Tyler? Tyler, you're not going to like it. Are you hearing me? Good. This is negative. And it's negative because we moved against the potential in our calculation for the electric potential. And our capacitance isn't negative. What this really is in the denominator, and I'm going to reverse it just so you guys recognize it, the capacitance is not a negative number. Capacitance is going to be a positive number. And I should have been more, but we're trying to just get an expression for the capacitance. And what I need in the denominator is the separation distance of the two plates. Haven't you noticed that that's been in the denominator of every one of our calculations for the capacitance, going all the way back to a parallel plate, which has the separation of the plates in the denominator? B minus A is how far away the two spheres are from each other. Right? With B being bigger than A. And it's been that way for every one of these calculations. Even when we had the one with the coaxial one from last week, we got an expression that had the natural log of a ratio of the two of the inner radius to the outer radius, which was still an expression of the separation distance of the two sides. So every single capacitor has something that has to do with surface area. Look at that. 4 pi A is a surface area. I'm sorry, 4 pi AB. If you think about what 4 pi AB actually is, you'll understand why that's an area. And for those of you who aren't with me because it's, 9:25 in the morning and all that, 4 pi r squared is the surface area, right? surface area of any sphere. So I'm taking instead 4 pi a times b. It's kind of like a weird average surface area of the sphere. It's not really an average, but it's kind of like an average. It would give us something that's kind of like the middle of the surface area. And then I'm dividing by a number that is straight out the separation of the two spheres. Now, that being said, something else that we could consider here is that we can also write this expression as 4 pi epsilon naught AB over, we can't do it this way. I don't want to do this. Sorry to bore you. We can rewrite this expression as 4 pi epsilon naught over 1 minus b, 1 minus a. We can leave it like this. Now, I know that your math teacher would yell about this one, right? Because they don't like having these expressions with fractions in the denominator of a fraction. But what this expression lets us consider is a limit as b goes to infinity. I know you guys are asking, does it matter if it's b minus a or a minus b? Let me answer that with a hypothetical. It's in the calculation of the capacitance, it should be the larger side minus the smaller side, the larger radius minus the smaller radius, so that the value of the capacitance is a positive number. Now, if we had charged the outside to be positive and the inside to be negative, we would have had a negative sign that would have developed because we were going against or with the field. The question here is that it doesn't matter whether the potential is an increase in potential or a decrease in potential. The same amount of charge is going to be moved due to that potential difference. Because of that, the value of the capacitance, the absolute value of the capacitance, remains the same. So we tend to express it in the terms that would demonstrate a positive value for capacitance. Is that okay, Savri? Karen? All right. Now, this idea that we could run this limit, if you look at what that means one of these fractions, the 1 over b1, is going to go to 0. And the other one's going to stay. So the limit as b goes to infinity is an expression for the capacitance of a single-sided capacitor. You see, this is a unique occurrence in that any sphere of charge has a capacitance and can be treated like a capacitance or a capacitor. Now, this doesn't require a shell around the first shell. If I have any conductor that is spherical in shape, it will store energy like any capacitor. And the amount of energy it will store will depend on how much charge there is, which means anything. If I can apply a potential to it or I can add charges to it, is going to store energy in the same way that a standard two-sided capacitor would, and it can discharge that energy. The Earth is a spherical capacitor. It has all of the properties we would expect of a capacitor. It's being charged up all the time. It's currently receiving incredible amounts of solar radiation that are in the form of charged particles. So instead of a potential difference being applied to the Earth, it's receiving charged particles directly from its environment. meaning that the Earth itself, as it floats around space, gets discharged all the time. This is actually a concern. When we come back from the moon, you're far enough away from the Earth where the capacitance of the Earth can discharge through your spaceship on its way back into the Earth's atmosphere. In fact, the discharging of the Earth against satellites is a real thing. The Earth discharges from its atmosphere into the stratosphere all the time. And it does so because it has an internal capacitance based on the structure of a spherical capacitor, which means the Earth basically is giving off electrical discharges to the space around it all the time due to the fact that it's a charged capacitor in space, and it is constantly being recharged by the sun all the time. Now, the Van Allen belts, which surround the Earth, oftentimes act as an exterior shell because they are belts that are created due to the magnetic field of the Earth, and they trap charged particles as they come to the Earth, which does produce a two-sided capacitor, as you would kind of expect if there was an actual conducting shell out there. Now, the Earth's electrical activity like this, although is measurable and can be hazardous to small satellites, it's nothing compared to some of the bigger planets, the ones that have really, really, really powerful electric fields. Jupiter is known to have an electric field that is so big it could be detected on Mars. And its magnetic field is big as well. So you get pretty incredible and intense electromagnetic interactions in places as far away as Mars and the asteroid belt. Jupiter's difficult to fly to because you have to model its electrical and magnetic properties when you're going to try and send a spacecraft to Jupiter to try and evade some of the more dangerous areas. In fact, Jupiter has this toroidal area of destruction. It's something that is inside the rings of Jupiter, but it's basically, I should draw that another color. It's basically a toroid. And I'm not sure I've ever used the word toroid before. Have I? A toroid is a cylinder that's been, a toroid is a solenoid that's been bent into a donut. Does that give you a feeling about it? So imagine if you had a metal ring and you placed wire wrappings around it, like so. You could create inside this ring a circular magnetic field. It's a toroid. You ever seen the arc reactor? Tony Stark and, the arc reactor. Yeah, they're trying to make it look like it's a toroid. His number of wraps per second, which was the stupidest phrase ever uttered in the MCU, was in Iron Man 2 as he's describing the inferior version of the arc reactor made by the bad guy. They're trying to demonstrate it as a toroid, but a toroid is the real thing. We use them all the time actually in transformers. Jupiter has a magnetic field that is circular about the outside of the planet, and it's like a toroid, but it's incredibly strong, fatal to almost all forms of life from the Earth. It would just rip stuff apart. But this toroidal magnetic field, we really have no idea why it's there. We just know that it's definitely a no-fly zone. It is a stay away from me zone all the way, and it's right inside the inner rings of the planet. All right, so back to the end of this. There are 3 kinds of capacitors. And I'm going to put a fourth here too. We've got parallel plate, with assumptions made. We just did spherical. Spherical one-sided. And we did the cylindrical, but you're gonna hate me as your teacher. I don't have time to pull the notes out, and I don't have it memorized. I know it's logarithm of b over a in the denominator. I know it's an epsilon up here and the length up here, but I can't remember if there's a 2 pi here or not. Should be in your notes though. I want to say it's 2 pi here, but I can't remember. I don't know if the pi canceled out or not. Come on, one of you. Be the best physics students today. Well, I don't know if it is or not, but I'm looking for the cylindrical. Come on, one of you, look at it. You did write it down, right? Jake asked a question. We went through the whole thing. Then they turned it into a magnetic field. That was Thursday. It was such a banger day. I've been told the word banger is a thing. Probably not in this context at all. Come on, Luke. I haven't heard from you yet today. Or Matt. Yeah, I think they just like log in, but just turn off, just roll over and go back to sleep. College is going to have a world of hurt for them in the future. Come on, Hannah. I know you took notes. It is 2 pi? Thanks, bro. How's that mullet coming? Yeah, I saw the pictures on Instagram. That sucker's a big boy. As you put, a solid unit. So, nice looking dog. All right, so these represent the 4 basic types of capacitors. Each one has a specific kind of assumption that has been made. And let's talk a little bit about those assumptions and then we'll be done. First, when we talk about parallel plate, you should remember the assumptions because this one's the one we did the most, but remember the size of the area is much bigger when compared with the separation distance of the plates. This allows us to ignore the effects of the curved electric field at the edges. So we know, though, that actual parallel plate capacitors will have a capacitance slightly less than our expected capacitance because they have a non-uniform field towards their edge. Again, actual parallel plate capacitors will have a slightly less capacitance because of the edge effects. And that's going to be true for the first 2 of these. Cylindrical capacitors, of course, we are assuming that the inner and outer radius are small when compared with the length of the capacitor. Same kind of thing we would expect for the parallel plate, that as you get towards the edge, we get a non-uniform field, so the total capacitance will be somewhat less. Spherical capacitances don't have limitations. This is the exact value you're going to get for the capacitance. The problem is you can't make one without having a hole in it because there's no way to charge and move charges from the inner surface to the outer surface. So the moment you put a hole in it, you create a place where you'll have a non-uniform electric field. So this idea of a capacitor is more theoretical, and you really, I don't know of any that you'd put into practice. But on the other hand, these two represent sometimes capacitors that you don't expect, because it suggests that any object that's charged can have values of a capacitance, values of a capacitor. An airplane flying through the sky, it's not spherical, but it is a metallic body. And because it's a metallic body, it probably will store charge, and that charge could discharge like a capacitor. I mean, a good example that is put into practice are fuel tanker trucks. Fuel tanker trucks are not spherical, but they have a metallic outer body that's usually all one big outer body. That outer body, being that it's metallic, does collect charges. The rubber tires scrape against the road, and it slowly charges the outer body of the fuel tanker. So that when the person who gets to the gas station is about to connect the fuel tanker to fuel the tanks in the ground, he has to discharge the truck ahead of time to discharge that capacitor because it's been charging the whole time that he's been driving. In fact, most fuel tankers drag a chain on their back axle that's in contact with the ground to allow a trickle of charge to be leaving the truck at all times. But before they can fuel the actual ground, they have to discharge the truck first. They have to put a grounding rod on the truck to ensure that it doesn't have any static charges, because a static charge could be quite detrimental when you go to place the metal housing of the fuel pump into the ground connectors. Believe it or not, this is an issue for your car when you go to fuel up. Have any of you stepped out of your car, gone to close the door, and shocked yourself? It doesn't happen as often here in Florida, but it happens, especially in the winter months when we're drier. Your car acts like a spherical capacitor, doing the same kinds of things we're talking about here. All right. We didn't grade the FRQs today.